Hello everyone, welcome back to our weekly CnosDB live show. In this series, we will discuss stream processing idea, some relevant implementations of stream processing technology in CnosDB. I believe today's lesson will be quite enlightening. Today, we'll pick up from where we left off in the previous episode, as there was some remaining content. In this session, we will mainly discuss the examples of practical SQL usage, following a general process. We'll use a flowchart to illustrate this process. Then, we'll examine how a given SQL string is transformed, parsed into a logical plan, and how its physical plan looks like. We'll also evaluate some real-world data for comparison. Finally, we'll explore the data after each processing step to understand the overall flow of this process. Let's dive into the details. We won't go through the content of the previous session together, but if you are interested, you can check out the last video in our previous series. In this session, let's dive right into an example. I have prepared a few simple and typical examples. The first one is a straightforward filter on a relatively simple table structure, consisting of a timestamp column and a name column. Our SQL includes a simple filter with a where condition. Now, let's explore how it is executed in the stream processing. Let's take a look at this diagram. The text might be a bit small, but if you record the data from the previous sessions, with the timeline and data points we used, the line represents the timeline, and at 12:05, there are 4 data points. This cycle after planning, resulting a logical plan in CnosDB. The logical plan begins a stream scan, indicating regarding from a stream table. The fields above are the names in our SQL, and we are setting the watermark to 00 milliseconds during stream table creation. Then there is a projection. Following that, there is a table write operation, indicating the insertion of data into another table after processing. Comparing this logical plan to the batch processing logical plan from the previous series, you can notice similarities with a slight difference. In batch processing, it starts with a TSKB scan, representing regarding from our KB table, but here it includes a watermark. Now, let's examine the physical plan. First, let's look at the initial node, TSKB exact. It's called TSKB exact because where we created the stream table, it specified the target table and the source table. In this case, it's another TSKB exact table under the public schema. Therefore, during execution, it reads from our internal table, which is another KB table, followed by repartitioning, filtering conditions with course batch exact, and the final table writer merge for writing into the target table. This SQL is relatively simple. In processing the data, for example, at 12:05 with 4 records, it filters out the records with dark, leaving only the records with cat in the output. If you are familiar with the principle of stream processing from our previous sessions, you should understand that after each processing step, the output for 12:05 would be the record from 12:02. For 12:10, both records would be output, and for 12:15, only the record with L would be the output. Since we are not using time windows or aggregation operations here, There's no state or related operators involved. Now, let's move on to the next example, aggregation. Aggregation might seem a bit complex, but it's straightforward. Consider the cycle. Select minimum time from stream table, group by name. This operation groups the data internally and finds the earliest appearance for each row. Looking at the logical plan, it starts with the stream scan, followed by a watermark, an aggregate operation for grouping and aggregation, and finally a projection and table write. Let's look at the physical plan. It includes a TSTB exact node for reading from another TB table, repositioning watermark and aggregate for grouping and calculating the minimum time. Importantly, there is a state restore operator involved. It is responsible for merging data from previous processing step. With this aggregating, there is a state involved due to the nature of the operation. The state restore operator retrieves data generated from earlier operations to merge with the current data. And this process repeats for each processing step, merging the already accessed data, followed by a partial merge, indicating a partial merging operation. After completing the merge is a swift dispatch of data has been processed. The aggregating operation is also considered complete, resulting in a state save to store to the result of the processing, dispatch of the data. Next is an aggregate operation for final processing, followed by a projection, correlates partition, and table write to the target table. Notice that the state save, which includes a watermark. This watermark is crucial for deciding which data to output based on the time, as we are using an update operation. Now let's look at the data. Suppose that at 12:05 I trigger the VP operation. The output data should look like this. For instance, based on internal aggregation and selecting the minimum time, let's focus on the earliest appearance of dog and cat at 12:02. So the output consists of two records, one for cat at 12:02 and one for dog at 12:02. Now for the VP operation triggered at 12:10, when the aggregation data is saved, 12:03. Because we have state storage, the records not only get output but also stored. For example, two more records arrive at some point after 12:10, and at this moment, the state stored data is taken out to merge with the current batch, resulting in a new merge. After this merge, the time is 12:07, and the system selects the minimum time, which is 12:02, the dog time. Therefore, at 12:10, the output consists of the not one record, cat at 12:02, and dog at 12:02, and owl at 12:07. Moving on to the VP operation, triggered at 12:15, the output includes a record for dog at 12:04, which is considered delayed data because we did not specify a watermark during table creation. This means we do not tolerate delayed data. So the record from 12:04 being delayed is discarded, and only the record from 12:13 remains after the merge. Next, let's move on and look at the next SQL operation. Well, the next SQL query involves a time window. For example, take a look at this SQL. This SQL query is based on a hexadecimal operation. Here, I use a dateBin function. Every 5 seconds, creating a window. Each 5 seconds forms a window. Then, a grouping operation is performed on this window, followed by a calculation of the first occurrence within this window. It refers to the earliest record within this window. For the internal market of this record, I used a function called first. Now, let's examine the logical plan. This logical plan is quite similar to the previous aggregation operation. The logical plan is essentially the same. It's also a stream scan, followed by a watermark operation. The aggregate function here is dateBin. There's also a first grouping. It involves grouping based on the result of dateBin. Then, a projection operation, which is followed by a table write. That is, writing the process data. After processing, it's written. Now let's look at the physical plan. This physical plan is essentially the same as previously mentioned aggregation operations. This physical plan is identical. So it also has a TSKB exam, followed by a repetition and watermark operations. Take note of the 0 milliseconds delay here. This is because we didn't specify it during the creation of the string table. It wasn't specified, so I won't tolerate. That means I won't tolerate any delay. Next is the aggregate operation. This aggregate operation is a local aggregation. After local aggregation, there is a repetition and a chorus batches. We won't dive into these details. This is just the function steps. It's like an auxiliary component. Then there is a state restore. It retrieves the data from the state store for merging, followed by partial merge. Then state save the process result is saved for the next VP processing. You can see a watermark here. This watermark is actually calculated. It discards data earlier than. Because our delay is 0, data earlier than this time will be discarded. And then there's the aggregate exact, which is the final partition. It's the final output, followed by partitioning, projection, and table write. You can see it's similar to the previous physical plan. Well, in this case, since it's kind of window operating, a window aggregation to be precise, in stream processing, window aggregation is quite common. It's not only in stream processing. In this database, window processing with time windows is also quite common. Now, let's take a look at the tape data, which is the same as before. For example, at 12:05, I triggered a VP processing. What should be the output? For example, based on this data bin, every 5 milliseconds is a window. So 12:02 and 12:03, all this data is actually within the same window. Then, it takes the earliest record using first. The content of this earliest record, the earliest time is 12:02. There are two records for 12:02. That's the 12:02 cat, and the data bin is 12 o'clock. So after 12:05 is processed, the input record is actually 12 o'clock plus a cat, a small record like that. Well, it outputs, and it will also be saved in the state store. Next, at 12:10, another record arrives. Now. At this point, it will first perform on. We can infer from this physical plan. It will first perform a local aggregation. A local aggregation on the machine. A local aggregation. After that, its result is actually at 12:07. A small record like this. It should be now 12:05 because it's every 5 milliseconds. Every 5 milliseconds is a window. 12 o'clock is one window. 12:05 is another window. Then this 12:07 happens to fall between 12:05 and 12:10 in this window range. So it will be a 12:05 window. That's 12:05, of course. And this record, after it's processed, later there's a state restore. So it's a 12 o'clock get, 12:05 out. Then with this 12 o'clock get record, it merges. And at the same time, it performs a ascending merge. This ascending merge operation, they perform a merge because they belong to different windows. So the output window is actually 12 o'clock cat plus this 12:05 out. Then after power merge is processed, there is a state save. So these two records will be saved in this state store. And finally, a final aggregation operation is performed. And its output, in fact, is 12 o'clock cat and the 12:05 out. Here it outputs, and the next time it processes, similarly, actually, we can take a look at these two records that arrive at 12:50. These two records, because the 12:04 record was discarded, it's delayed data. Just remember, top 30. Also, to perform a window operation, it falls within the window at 12:10. And at the same time, the data stored in the store before is taken out. That means it's a 12 o'clock cat, then there's a 12:05 out. And here, we have another 12:10 out. So in essence, at 12:15, after processing, it inputs this three records. So according to this one example, let's talk about cycle. This cycle. After going through the planner and being planned into this lotter plan, then transforming into this physical plan, and at each step, what the actual data output is like. Actually, you should not be able to understand the entire process of our stream processing. Today, we cover these three typical examples, and then let's look at regarding our current design. There were actually some issues initially, and for these issues, what solutions did we come up with? First, there is the issue of stream job metadata. How its original main information is stored, where it is saved, and for this stream task, for example, after the machine is down, which node should be responsible for restarting? Because in our cluster mode, this fast forwarding is stateless. So we encounter this problem, which node should catch up? The second issue is related to structured streaming. As we discussed earlier, each VP processing in structured streaming will record the WL and commit log, and also the state store. Initially, it was HDFS, and later it was changed to RocksDB. So each VP processing involves this relatively time-consuming operations. WAL involves I/O writes, commit log, and other operations involve I/O. But recording this state also involves I/O. So this might be a kind of resource consumption. So in our time series scenario, we want to minimize this kind of consumption. So how should we reduce this kind of consumption? Another thing is our current internal table, the TSTB table. Actually, it's a standard table with a unique feature, and it has a time column. All internal tables must have a time column. So when consider our internal table as the source table for streaming processing, because streaming processing needs to handle delayed data. How do we deal with this delayed data? It requires an offset. And this offset is independent of the event type. So On our TSDB table, what should we use as an offset? Well, these are the main three questions. Let's go through each one and see how we can solve them. First, let's look at how we can solve these problems. The first one depends on different scenarios. In the cloud, we have specialized tools to handle streaming tasks. We separate them into different blocks, one for streaming tasks, one for batch tasks. It's like giving them tags. We have specialized tools to handle streaming task blocks, so users don't need to worry about these details. Also, the Red Hat log, WL, commit log, and state parameters need to be remembered. Initially, we thought about recording data in our method, but considering that method not only needs to store original data, but also other things. And in a cluster, there's one method cluster for each CnosDB cluster. And possibly, a method may support multiple clusters. So the method's load becomes high when the cluster size increases. If it's not just one node, but multiple nodes across different places, and considering an increase in the number of streaming tasks, the method's burden increases. Initially, when considering using RocksDB like Flink or Spark, but we didn't want to increase the capacity of our architecture. So we thought of a way to simplify the WAL and the commit log. We only record the offset once, only record this offset and state stored in memory. We also considered not recording it at all, and we came up with a solution. After processing each time, we delete this because each time window processing will eventually end. It's not possible for a time window to span multiple watermarks processing. When the watermark exceeds or is earlier than the watermark, the window is discarded, indicating that the window has already been processed. So at this point, we record the offset. But there is a potential issue. For example, in the current batch, if I process a portion, and this window is not fully processed, it might arrive in the next batch, and the data for this time window is still in memory. It's saved in my memory, and this is where the state store comes in. Why restart the task next time? There's a chance this batch of data might be processed again. This is actually a problem, but initially, when we designed this, our things was idempotent rise. Our internal table is a good fit because it inherently handles duplicates. So even if it's processed redundantly, it will be overwritten. In this case, we only need to record this state in memory, and we don't need to persist it. And as mentioned earlier, when we process data, we delete it after each processing. However, for our scenario, this is not an issue. So essentially, the state store doesn't need to have the persistence. And for the commit log, we only need to record the offset after the entire time window is processed. This might help reduce some resource consumption. Now let's talk about the choice of the offset in the KB representation. And first, we use the time column as the offset for the streaming table. However, this may not handle delayed data well. Later, we developed support for subscribing to offset in TSDB tables. This feature is possibly not only available in our enterprise edition. Integrating this subscription into our streaming table serves as a data source for streaming processing. This is supported in our enterprise edition. During the development and design process, we consider these issues while others are more straightforward details. Well, in today's lesson, we covered the processing flow using typical examples and shared insights into our design considerations. Thank you for your time. And once again, as you all know that CnosDB version 2.4 is out, and you can try and let us know. And our CnosDB Cloud is fully published. And you can join our Discord in our link, and you can join our cloud list, and you should be able to see the link in our video. Thank you. See you next time. Bye-bye.